For today's video, we'll be looking at properties of limits. Our first one, if we have two separate limits, if we've got the limit as x approaches a of one function f of x and saying it equals some number L, and a different function approaching the same value of x equals some number m, if we take the limit of those two functions added together, then that overall limit is the two limit values added together. So for example, if our limit as x approaches 2 of x squared plus 1, that would end up equaling 5. And our limit as x approaches 2 of, say, like negative x plus 4, that would end up equaling 2. What our theorem is saying is if we take the limit as x approaches 2 of x squared plus 1 plus negative x plus 4, that should just end up equaling 5 plus 2, which is 7. So in other words, if you're adding separate functions together, you can just take the limit of the whole thing. Or you could do them each separately and then add those limits together. You'll get the same answer either way. Here are a bunch of limit laws. You can either pause and copy them down, or they're also on textbook pages 99 to 101. All of these laws rely on the fact that the limit of f of x and g of x need to exist. If one of those limits does not exist, then these laws do not apply. The first one is what we just saw, our addition one, and the same would apply for subtraction in number 2. Number 3, if we have a constant that's multiplying a function, that says that we can pull that constant out, take the limit of the function, and just multiply it back in. So, for example, if you had 7x squared for the function, you could do just your limit of x squared, see what you get, and then multiply the limit of just x squared by 7, and that'll be the same as if you took the limit of 7x squared. Number 4, we have multiplication. You could do it separately for each of the functions when they're being multiplied. Same is true as for division. The one thing you have to watch out for with division is the limit of the one in the denominator cannot equal 0. Because if it's 0, then we would be undefined. In number 6, if we have a function that is raised to some integer, that's saying we could take the limit of the base function and just take our answer and raise it to that same power. So for example, maybe this was like x plus 2 to the third. We could take the limit as x approaches a of x plus 2, find what that answer is, and then raise that answer to the third afterwards. You'll get the same thing. Our limit of a constant is just a constant. So if you have the function like y equals 2, it doesn't matter where you pick your x value you're approaching to, your limit's always going to be 2. In 8, if you have just y equals x, well, the y values are going to approach whatever x value you're getting close to because y is always the same value as x. That's what number 8 is saying. Nine is pretty similar to 6, just in 9, we just have a single variable x, not necessarily a whole function. And it kind of combines 6 with 8, because if you have that single variable x, that should just end up approaching whatever x value you're approaching. Like if x is approaching 2, that base should just get close to 2. And in 10 is pretty similar to 9 because roots can actually just be written as exponents. So it's pretty similar to 9. We just need to assume that our values are under a radical are positive if we're dealing with an even root, like a square root, a fourth root, because those negative values would not be in the domain if it was a square root or fourth root. And then 11 is similar to 10, just we have an actual function underneath the radical. So again, you can either pause it and copy these each down, or they're also in the textbook on pages 99 to 101. So now we'll look at applying some of those properties. We want the limit as x approaches -2 of f of x plus 5 g of x. Well, our properties tell us we can take the limit of f of x to start out as x approaches -2. F is our red one there. So as x approaches -2, our y values are getting closer and closer to 1. It doesn't matter that at -2 the function is really 2. Remember, limit is as you're getting close to that x value. So as we get close to that x value, our y value gets closer and closer to 1. So we know that's just 1. Plus, we know our constant rule. You can just pull the constant out and take the limit of the function itself. Once you have the limit of the function, just multiply it by the constant out front. So we're really just going to look at the limit of g of x as x approaches -2. Well, these same arrows here on the x-axis, as x approaches -2, we see, oops, that was not on the x-axis actually. Here's your x-axis. But as x approaches -2, we see that g is going closer and closer for our y values to -1. So we'll put -1 in for g's limit as x approaches -2. And now we just multiply and add. So 1 minus 5 will give us the overall limit of those two functions added together is -4. Another example, we're going to look at one with multiplication. Our limit as x approaches 1 of f of x and g of x. Well, first, let's work down on the bottom with our left hand and right hand limits. So the two left ones there, we're working with f of x. So f of x is the red graph. As we approach 1 from the left, so here's an x value of 1 from the left, notice our graph of f of x is getting closer and closer to 2. If we approach the next value of 1 from the right, f of x is also getting closer to 2. So therefore, in our overall limit we're looking for, f of x times g of x, because our left-hand limit for f of x equals our right-hand limit for f of x, we know therefore our limit of f of x is just 2. As we now try g of x, as x approaches 1 from the left of g of x, notice g's function is getting closer and closer to -2. And as g is getting closer and closer to x, or to 1 from the right, our y values are getting closer and closer to -1. Notice our limit of g, the overall function, now does not exist. Our rules, we said, only applied if each individual limit exists. Because now the limit of g of x does not exist, this overall limit also does not exist. Now, there could be some cases where it could exist. Okay? Overarching, our theorem does not necessarily become true when one doesn't exist. To check see if it does exist, you look at your left hand and right hand individually. So look at our two left-hand limits. We have 2 and we have -2. Well, together, 2 times -2 gives us -4. So you can think of it as your overall left-hand limit for the function is -4. The right-hand limits overall, we have 2 and we have -1. So your overall right-hand limit is -2. Notice still, -4 and -2 are not approaching the same from the left and the right, so therefore we still do not exist. the fact that g of x's individual limit did not exist, if we had still had them after we multiplied our lefts and our rights together to get the same number, we could have still had an overall limit existing. Okay, but the fact that g of x did not exist does not allow us to just assume that it's going to work. We have to check and see if it will work. And in most cases, it's not going to. An example of how it could have worked is, say, f of x's right-hand limit was 2, or left-hand limit was 2, and g of x's left-hand limit was -4. And then what if this was now a 4 instead of a 2? Well, now neither limit exists on its own, but both of them, when you multiply, we would have 4 times -1 now to give us -4, so they would match up. So then our product limit would work. Okay, so basically if one of them does not exist on their own, you got to kind of examine it a bit further. Now we have a quotient. So we'll look at our limit as x approaches 2 of f of x on its own and g of x on its own. So when we're getting close to 2 on the x-axis, f is getting to somewhere it looks like around 1.5 or so. So we know we have about 1.5 on the top. But on the bottom, g of x, you can see those y values are getting closer and closer to 0. We had in our theorem that it only worked if g of x's limit, or in other words, the limit that, or the function that was in the bottom, because it might not always be g of x in the bottom, if that limit's 0, then our overall limit did not exist. Okay, so this one does not exist because we would end up having 0 in the denominator. So we'll look at now evaluating some functions algebraically. If a function is defined at the value where you're taking the limit, and it is continuous there, then you can just do direct substitution. This function here, 2x squared minus 3x plus 4, is a parabola. Parabolas have domains of all real numbers. Therefore, they're defined everywhere. So this is something to evaluate the limit we can just plug in. So we'll do 2 times 5 squared minus 3 times 5 plus 4. 5 squared is 25, times 2 is 50. We'll have minus 15 plus 4. So in the end, we will find that our limit is just 39. So that's always the first thing you want to check, because direct substitution is pretty easy. Is the function defined at that value? Are there no jumps or holes at that value? Then you know you can just do direct substitution. Now, you would recognize if there's jumps if you had some type of piecewise function. So here's another example. If we try to do direct substitution, notice we will get a 0 in a denominator. Therefore, we cannot just do direct substitution right now. If that is the case, we want to try and do something to rewrite the function so that we can do direct substitution. One of the common things we'll do is we'll try and factor and cancel things out. The numerator factors into x plus 5 and x minus 4, and now we're over x minus 4 still. Well, the 2x minus 4s divide out to 1, so we are just left with x plus 5. This is now something that we can do direct substitution with. We'll plug our 4 in for x, and therefore our limit of the whole thing is 9. So this fact that allows us to do this is actually another theorem that we'll have. If you've got two functions, f of x and g of x, that are the same but not necessarily when x equals the value you're approaching. Then your limits would be the same. So really what we did is we wanted the limit as x approaches 4 of x squared plus x minus 20 over x minus 4. When we canceled out, we actually took the limit of x plus 5 as x approaches 4. These functions are identical except when x is equal to 4, because in the left-hand function, when x equals 4, it doesn't exist. It's not in the domain. It's undefined there. There's a hole, in fact. So this tells us that those limits are equal. Now, just so you can see it in a table, I put each of the functions in a graphs page and did a Control-T to look at the table. The left-hand column, the blue ones there, are our original function. The right hands are our new function after we cancel out the x plus 5. If we scroll through, look, all the y values are the same except for when x is equal to 4. For our original, it's undefined, and the right-hand one, it's 9. So our theorem told us that if it's the same everywhere except for when x equals 4, the value we're looking for the limit at, then we can just use the limit of our new function after we canceled out. So this is what allows us to do that. Okay, a couple more examples. Remember, our first thing we want to always try is direct substitution. In example F here, the problem we could run into is if when we do direct substitution, the denominator will be 0, because then it would be undefined. So let's test the bottom. We've got 2 squared plus 6 times 2 minus 4. That'll give us 4 plus 12 minus 4. So we'll just get 12 in the denominator. So therefore, this is going to be something we can just do direct substitution with. So we'll just also plug into the numerator, and we'll be able to find our limit. So we'll have 2 times 2 squared plus 1. 2 squared is 4. 4 times 2 is 8. So we'll have 8 plus 1. Or in other words, we'll have 9/12. And if you wanted to reduce it, it reduces to 3/4. So this was a case where we were able to do direct substitution because it was defined where we were trying to approach, where x approaches 2. Now in example G, if we try to put a in for x, so remember whatever x is approaching, you want to try and plug that in. If we put a in for x in the bottom, a squared minus a squared is 0. So we cannot do direct substitution right now. So just like our last theorem we saw on the previous slide, we want to try and do something that can create a new function that is equal to this everywhere except for at a. And then we can just evaluate our limit for that one. So the method we've learned so far is to try and factor. Well, if we factor the top, we know we'll have x times x, and we'll need an a times a. In order to get a negative 2ax, they will both have to be negative, because we'll get negative ax for our outside terms, negative ax for our inside terms. The denominator is the difference of 2 perfect squares. So that's just x minus a and x plus a. Because if you were to FOIL it out, the outside terms would be positive xa, the inside terms would be negative xa, so they would add to 0. Now we have something that can divide out to 1. We've got a pair of x minus a's, giving us just x minus a over x plus a. Now when we sub in a for x, it is defined in the denominator. We would have a plus a. So we can just go ahead and plug in. We'll have a minus a over a plus a. That's 0 over 2a. 0 divided by anything is just 0. So our limit for this function as x approaches a is just 0. That's all for today's video. We'll see you next class, period.